we were talking about GMC filter. So we implemented GMC using the GM and C blocks, right? Whenever there is a capacitor between a positive output to positive input, it's creating one in derivative plus some multiplication number. So something like this is going to give you two things, K1 plus K2S. If you have a simple GMC block, the output is multiplied by K1. This is multiplication. If you want to make integration, just add one capacitor at the output, it will give you integration. This is derivative. And if you want to add so many number of GMs, you can add them by shorting them. So we learn all these things, and using these these things we have drawn the whole circuit. But the most important part was how to actually make those GMs, because in this box it's equal to GM, where GM is nothing but I out divided by V in. So I want to implement that. Previously we studied some of the structures which are first order, second order, biquadratic and GM's implementation. However, the transconductance determination is very important thing. This has not been done till now. I am following same book, John Martin. Now the fundamental thing which we can use is this one. We are talking about this right last time. So what do you think? This is okay, or are you convinced with me or no? You did something right at your home or no? Home means hostel. Hostel is your home, right? So when you are adding one resistance, this becomes linear, because I'm expecting that GM for any value of V in, it has to be linear. So how to make sure that? Hmm? Yeah, source degeneration is going to give you linear, but how? Do you know this? Now you found out or not? Yes or no? I'm asking you. We learn it in E512. That is what I told you. So have you gone through that lecture, or even I suggested to read Behzad Razavi, the red colored book? Yes or no? Just tell me. Hmm? Shubham, you read it. So now prove it. Then so very quickly just look at this thing. So just for biasing a BJT amplifier, you can use such kind of scheme where there is a resistance, but the only problem is, what is the problem in this one, by the way? If I am doing, or if I am making this VCC minus VX divided by RB as current IB, that is fine, right? I can supply IB current from here, but is there any problem here? Yeah, PVT problem, because this RB is actually temperature dependent, right? So it's not a good thing. So what I'm saying, and you can solve these equations, you can see that there is a beta factor and temperature, so it's also depending on the beta of this Q1 anyway. So one can use everything in a ratio, like resistance. So what is going to, this is fine, right? So Vx is nothing but R2 times VCC divided by R1 plus R2, right? Yeah. But what about the current IC? Because that is the quantity we are looking for. So IC is nothing but IS exponential times VBE by VT, right? So VBE is already known to us, that is Vx. So this is VBE divided by VT. But here the problem is it's exponential, it's not linear. So the answer is the degenerating resistance at emitter, or maybe in the case of MOSFET you can have a source degeneration. So RE exhibits a linear resistance, linear relationship. You can check that IE is nothing but VP divided by RE and 1 by RE times VP is nothing but this is VB. This is actually VB, right? Look at this. This is VB, and VB minus VBE is equal to VE, right? You agree with me, right? So when you are doing this, your whole equation is a linear equation. There is nothing like exponential, nothing like beta, right? So the relation between VBE versus IE or IC is linear. It's controlled through a resistance which is acting as a feedback, right? So this is what I was asking you last time, right? So if you are using a resistance at the source side, you may have the linear relationship, and when you are looking at the output side, let's assume that you are looking at the output. One side it's positive, one side it's negative. If this is negative, if this is positive, if it is going in positive direction, then this current is going to be negative and you will have the current flow from this side. At that time this is going down, so current will be in different direction. So you can see the loop of the current which is flowing through two things. Two two things are two transistors Q1 and Q2 and two resistances RS by 2, RS by 2. If you are adding all of them, you are going to see this is 1 by GM, this is 1 by GM. So in total you are going to see VI divided by IO1 in terms of VI as VI divided by 2 GM, 2, actually it's 1 by GM plus 1 by GM plus RS by 2 plus RS by 2. So in total you are going to see 2 by GM plus RS, right? So GM is nothing but 1 by 2 GM plus RS. This is the thing, you can have it, and that will be the linear. This is a linear relationship. The only thing is GM we have not considered. Just look at this. GM is also non-linear quantity. Is it non-linear or linear? How did you get that non-linear? Right, so when you are doing this, GM is equal to 1 by what I'm making, it's mu n C ox W by L VGS minus VTH, right? So you can call all of them as one factor K, which is constant. So it's not non-linear, it's linear. Look at this. Look at this equation. GM is changing with respect to VGS in linear fashion, in saturation. Look at this. GM is applicable in saturation, by the way. If you are following this equation, it's linear. Hmm? Yeah, so how you are taking this, it's the most important part. What part you are considering as constant, right? That is what I'm saying. If you are considering W by L constant, no problem, right? For a constant current and constant W by L, this will be the effect. Your point is correct. You might have three different possibilities, right? Which we have discussed in E512. But if it is not the case, and if you are wisely doing all these things, then you are going to have the linear relationship, right? So as I told you, like if there are RS by 2, RS by 2, you can replace that RS by 2 as one RS, and two sides there are two currents I1, I1. instead of having 2I1, right? In this case also you are going to have the same transconductance which is linear, right? Considering the fact that the current is constant, look at this, what you are saying, square root of id and all. So if it is constant, there is no problem. Current is constant, w by l, everything is constant. You are just playing with the voltages which is at the input side, vgs, which is varying, right? So in that case, transconductance is also linearly controlled by a resistance which is rs. Okay, so in terms of linearity, the source degenerating a differential pair with a resistor linearizes the relationship between differential input voltage and output current. The result is a transconductor with a value approximately equal to the degeneration resistance. Now, uh, if 2 by gm will be in some ohms, right? Hundreds of ohms. Whatever RS you are going to keep here, it will not be in 100 or 200. You are going to keep something like kilo ohms or maybe 2 kilo ohm, 1 mega ohm. So then the factor which is controlling the whole linearity is not this one. It's only RS, or it's approximately equal to RS, right? So this is going to happen, and that is what written here, right? So for both the circuits, this is fine. Here, what this book is following, RE is nothing but 1 by G. Okay, just for your information, that's why I kept this slide, just to make sure that RE is 1 by GM, right? This is for BJT, by the way. You can see this is BJT, where you are going to have one resistance which is actually 1 by GM, but we are going to redefine it as RE. So one more better thing is, if you want better linearity with high value, you need to make the feedback for more accurately reproduce the input voltage across the degeneration resistor, or further improve the linearity for transconductors with fixed resistors. So if you want to improve better in terms of linearity, then you can apply feedback, right? Feedback is the best case. It has to be, of course, it's not written here, but it has to be negative feedback, right? So one of the, are you following this till now? Okay. So if you're following that, then in the feedback, what I'm doing, I'm using something called regulated load or regulated connection. Some people call this one as also auxiliary op amp, where gain of this loop, if you remember, it has to be multiplied with the gain whatever is there in this op amp. It might be even a single stage op amp, right? It's not compulsory that you are using just, you know, two stage, three stage. Instead of this, you can use this one also. Here it's Vi, and the this is plus and this minus is actually connected to, and this minus is connected to, I need to make differential actually. Anyway, so you can make that and you can find out this. Here the only thing is, whatever Vi minus you are giving, the Vi minus will be here and Vi plus will be here, which are actually differential by nature. When I'm saying differential, means 180-degree phase shifted, right? This will make sure that this is actually in between, it's a virtual ground by Rs by 2, Rs by 2, right? So this is going to happen, and this is going to work for your better linearity, right? So from here to here, when you are going to see, it's not only 1 by gm, but it's also multiplied by a0. which is going to make sure that your impedance is actually improving, right? So other than that, this resistance can be made using a transistor, which is a triode. So if I'm connecting these connections, let's call this one as A point, this point is B point. If this is A and this is B, if I'm connecting them such a way that the resistance with respect to VAB, or maybe some voltage of input, this resistance is actually linear. This is only possible if I am making this transistor in triode region, right? In saturation, it's saturated one, right? So we can use triode transistor, and for that it can be used in place of fixed resistors to make transconductors tunable, although their linearity is generally reduced. So we can do that where its equivalent resistance is equal to this one, where this thing can be replaced by K, right? If W by L is actually constant, if the current is also constant, then this is going to be happen, otherwise no, right?
So why linearity will reduce if it is work as the same as the resistance?
It's difficult to get same resistance, that's the
All
problem.
the time.
All the time, all the voltages I should say, it's equivalent to, we are doing this actually.
Yes, sir.
So it's a potentiometer kind of thing. So for a given value of the voltage, you may get what you may get something else than what you are expecting. So there may be some delta change. The delta change is actually, instead of this, you might get, it depends. So this is one circuit where this transistor has been kept with some voltage called VC, and through which you can tune and you can find out what is VO by IO by Vin, right? So that will be equal to the one which has been given. I'm telling this, or I'm going to this conclusion because if you remember the previous slide where I0 divided by Vin, which we are going to call the big GM, is equal to 1 by 2 GM plus RS, where RS, if RS is much higher value than 2 GM, 2 by GM, then this will be approximated as 1 by RS, right? If it is 1 by RS, means you are going to see this is equal to 1 by RS. 1 by RS is nothing but a triode resistance which has been kept here, or which has been derived from here. 1 by K times VGS minus VTN. So it's 1 by K times VGS minus VTN. But VGS and VTN, or VGS and this ratio, are of ninth number transistor, which is here. So it will not depend on anything else, but you can find out the answers directly, right? Other than that, some people may like to use transmission gate kind of structure where PMOS and NMOS are in parallel, whose resistances are as follow. So one one is like this and one is like this. If you are, so one is for NMOS, one is for PMOS, for the resistances with respect to input voltage or the controlling voltage, then you're going to see result like this, because they are in parallel or they will add together. So it will not be exactly here, but it will be a little bit with DC shift also, right? So the most important part here is when you are writing a GM, is equal to K times VGS minus VTH. But I am saying that the bigger GM, which is between this point and this point, and which is actually coming like this, where two transistors are in parallel, which needs to be taken into account. So what is happening? IO1 is equal to, in this case, IO1 is equal to RS1 and RS2, which were coming from these two transistors, and because of these transistor, you are going to see RDS3 in parallel of RDS4. It's similar to what we have done in the previous case, where we have done this thing, right? So this RS has been replaced by two transistors which are in parallel. This 2 by GM is replaced by two resistances of RS in terms of RS for Q1 and Q2. So it's RS1 plus RS2 plus parallel combination of two resistances. So that is going to give you GM. But I want everything in terms of constant terms. So in constant terms, what I can do, I can write down RS1 and RS2. So can you help me in writing down RS1 and RS2? Right, so this will be 1, this will be 1. You can call this one as K2 VGS2 minus VTN, right? Similarly for RS, you can write down RDS3. If you are replacing all of them, the GM is equal to something like this, where it's 4K1 K2 K3 divided by 4K1 K3. When you are doing so, all these things, I1 is equal to K1 times VGS1 minus VTN square. This is also the square law equation, if you remember. It's same as what we were writing. The only difference is we are going to call K here as some constant. But look at these two K in terms of GM and in terms of normal current. Both the constant has difference of 2 basically, right? So when you are doing all these things, you can find out I1 and you can find out VGS1 minus VTN, and you can find out VGS1 minus VTN in terms of current and K1, and you can feed this here. So that was the equation written in total. But these are the playing with the equations, and you are finding out some closed form equation, right? Hmm. Hmm? TS. Yes, they are RS1 and RS2. RS1 and RS2 are equal to 1 by GM of a respective transistor. Let's call them as, let's, so the way he made it, he made small RS, right? So traveling from here to here, there are three things I am seeing. One is RS1 from here, RS2 from here, and combination of these two transistors which are in parallel. And as we know that it's actually triode resistance, so triode resistance will be RDS, right, or the on resistance. So that is the one has been kept here, and that resistance value is nothing but this one, right? So you can separately do same thing, because look, you have kept one diode or kept one transistor which is actually tunable. So instead of that, what you are doing, you are keeping two things on top of it, on top of actually two inputs, right? So when you are doing this, your current is nothing but id mu and c of w by l, and this is the one if this is in triode, right? So if that is the case, so it's all about playing with triode and saturation. So when do you want triode or saturation, it's up to you. When you are doing that, then you have to write down this equation, and if you are writing down this equation, you can have gm is equal to mu and c of w by l1 times vds, which is actually the one which is coming from here, because that is a whole input value, and which is derived from here. So current which is flowing through here, it's some gm times vds. Okay, so it's all about fine. So sometimes you are implementing active transistor. When we are saying active, it's actually for the BJT. So as this book is also talking about BJT as well as MOSFET together, so it's that's why this word is coming into the picture. Remember, active in BJT is equal to saturation in MOSFET. However, there is one more term, saturation in BJT is equal to triode in MOSFET. So saturation in both the transistors are exchanging their word, right? So remember that. So when we are doing all these things and we want to keep active mode CMOS pair, it might be in this way, where one is NMOS, one is PMOS, or you can play with both as NMOS, both as PMOS. But I'm giving you one example that two transistors are in actually cascode or the active mode. So that will be equal to a big transistor whose input is VGS equivalent, it might be plus and minus, and this will be some VDS equivalent, which is between this point and this point, and the current which is flowing through this one will be equal to K equivalent VGS equivalent minus VT equivalent. For finding out this, you can find out the current from both the side, which is Kn VGSN minus VTN square, and other sides Kp VGS VSGP plus VTP square. This is written for this transistor and this is written for this transistor, right? When you want to find out an equation where K equivalent has to be in terms of K and Kp, can you do that, or is it possible to find out? Look, I have three equations where these two currents are same, or all three currents are same, all id are same, right? And they are written in terms of K times VGS minus VTS square. So you have to rearrange them such a way that you are going to get this equation. It's playing with just equations. So are you able to find out this equation or not? So when I'm combining two transistors and I'm calling them as one big transistor, it should give me this current, right? This has been written with common sense, but I'm saying how much what should be the relation between two transistors. Let's try. It's the derivation is already given in book, but let's try maybe. maybe the solution can be seen in the book. I am not going into that. Okay, I'm moving to forward. If there are two different transistors and they're exactly matched, when we are saying the matched one, do you understand what do you mean by matched? What is matching? They're carbon copy. Matching means carbon copy. They are matched. Sometimes when I'm saying matched, it's not exactly carbon copy. It's one side, let's say multiplier m is equal to 1, another side m is equal to 3. By the way, w by l are exactly same. I'm just playing with multiplier so that they are having the matching geometry. That is also called matched one, right? So w and l both are same here. This is also same. Just it's a multiplier. When we are saying multiplier, those many number of transistors are in parallel. Similar to that, there is something called fingers also. It's same thing. They're making so many number of fins in parallel, right? That is also we know, right? So we learn something called two transistors in cascode if two transistors are somewhere else. So what we can do, id1 is equal to k times vgs minus vt square. Similarly, id2 is equal to k times vgs. So id1 is equal to so id1 is k times vgs minus vt square. id2 is also same. Let's call it k2 times vgs, or let's, because they are matched, so it has to be same, vgs minus vt square, right? Now I'm interested in finding out id1 minus id2. So id1 minus id2 will be k vgs minus vt square minus vgs minus vt square, right? So it will give me vgs square minus 2 vgs vt plus vt square minus vgs square plus 2 vgs times vt plus vt square, right? Anything is wrong or
Last.
so then it becomes everything is zero. I made any mistake? Okay. If we are keeping vgs1 and vgs2, then this will work. vgs1 1 2 2, vgs1 vgs2, right? vt are same, right? So then we are going to have something like vgs1 square minus vgs2 square plus 2 vgs1 minus 2 vgs1 times vt. Same thing, you can do it in your notebook also. You may make mistake, right? So when you are solving this, it's vgs1 minus vgs2 times vgs1 plus vgs2 minus 2vt times vgs1 minus vgs2. That is going to give me k times vgs1 plus vgs2 times vgs1 minus vgs2 minus 2vt. No, this has to be minus and this has to be plus, right? right? Are you getting same result? So remember this, whenever there are two transistors, anywhere they have been kept, there are two currents ID1 and ID2 for a different VGS1 and VGS2. The current ID1 minus ID2 is equal to K times VGS1 plus VGS2 minus 2VT times VGS1 minus VGS2. You can keep this with the highlighted one and you can keep it in your mind, because thereafter we are not going to derive it. We know that ID1 minus ID2 are depending on VGS1 and VGS2 with this relation. This will be useful for finding out the GM factor. I'm interested in find out GM. So now what I'm doing, I'm adding something here with the ground. Earlier they were not connected with each other, but they were, yeah. So they are connected with each other by ground. Source is connected to ground, and one side you are giving VCM plus Vi by 2 and VCM minus Vi by 2. This is the differential signal, right? If you are doing so, ID1 minus ID2, so what will be ID1 minus ID2, by the way? K times, so you have to follow this equation. If you forgot, then you can write down this. Now let's replace these quantities. So VGS is VCM plus Vi by 2 plus VCM minus Vi by 2 minus 2VT times VCM plus Vi by 2 minus VCM minus Vi by 2, right? Plus Vi by 2, right? So this is correct. So K times 2 VCM minus 2 VT times Vi, so that is going to give me 2K times VCM minus VT times Vi, right? So if that is ground, if there is no ground, then you have to have VSS also in your picture, right? So by mistake I took it as 0, otherwise it will be VSS. So GM is equal to 2K times VCM minus VSS minus VTM, right? So now can you find out for this one if there are floating voltage implementation, because I'm looking at different possibilities where you are going to have the GM. We started with two transistors, now we are adding like one transistor. We in one case we connected both the source to 0. Now we are connecting two different potential where it is much more better than or linear than previous one. Just look at this. The previous case, the GM is nothing but 2K times VCM minus VSS minus VTM, right? From here you can find out this one, that these two quantity when they are in ratio, you are going to have GM. So here still there are some of the complicated things like VCM is there, or you can say VSS, VTN, all these things are there, but still they are constant. If you can maintain this constant term, there is no problem. However, in reality, constant DC is not possible, right? You will have some fluctuations. So I'm finding out some more technique which is going to give me linear relation. I'm adding, some cross coupled thing where one is Vx plus Vtn, one is Vx minus Vx plus Vtn. So In that case, can you find out the relation? For your information, ID1 minus ID2, if they are for any transistor, you are going to get K times VGS1 plus VGS2 minus 2VT times VGS1 minus VGS2. You can try in your notebook because now derivation is easier afterwards. Just you have to plug and play all these values. So VGS1 is this one, and VGS2 is this one. What is connected at source you need to add, of course. You have to look at the polarities where they are connected. Yeah. So did you get this answer? Yeah. So if you got this answer, then it's little bit easier than what we had earlier, right? So it was little bit complex terms in terms of like VCM, VSS. So it was depending on different fluctuations also. Like you may have VCM, VSS, they are fluctuating. However, in this case, it's only Vx which is the one which is with you. You can design it using maybe using somewhere from capacitors where you can store Vx plus Vtm. It might be some value, right? Now, other than that, there are more possibility because sometimes you are interested in finding out the larger GM. So, if you are interested in some like GM of some more only, maybe one more or maybe even some milli when we are saying, or sometimes 1 by mega ohm. So when we are saying large implementation, it goes with the actually it's smaller one. It's not actually the larger one. Larger means it's going to give you this value, denominator value, bigger one. So 1 by mega ohm means it's a micro mho. That is what you want to implement, right? So there is one possibility that you look here. It's difficult to make this Vx and Vtm. you have to use a capacitor through which it will be having charge of Vx and Vtn, and for that you have to take the charge of even Vtn from these two transistors. You have to find out what is the Vtn and you have to keep it on some capacitor plate, right? One side you can keep maybe Vtn, another side you can keep maybe Vx. So, or maybe you can keep two capacitors in parallel where one of them is charged to Vx, one of them is charged to Vtn, right? So you can do this, but it's a complicated sometimes, right? So it's not giving you guarantee also. So rather than doing that, let's implement that with a cross coupled or extra transistors where both are NMOS. Look at the configuration. Both the input transistors are of K and other transistors are of NK. So if these are 1 1 and if I am choosing N of something like 5, so this will be 5, this will be 5, this will be 6 times IB, 6 times IB, where IB is nothing but the current flowing through this branch, the bias current. So in that case, ID1 minus ID2, you can again find out through the equation which is already known to you, which is nothing but VGS K times VGS1 plus VGS2 plus minus 2VT times VGS1 minus VGS2. Just you have to look at the gate and source voltages. If you look at them, you can find out a GM which is controlled by NN, value of N and N plus 1. But you have to make sure that all the setup will follow such kind of thing. Then you can have the value of large GM. Otherwise, it's little bit difficult, right? So now I'm not going into how to do this. All these derivations are given in book. Just you have to play with the VGS. What is available at gate and what is available at source. Just you have to write down that. Then you will find out these equations, right? Similar to that, look, the previous case, we are keeping this something floating. That's why it was floating voltage implementation. However, in this case, I am connecting them to somewhere to the load, and through a transistor, I am keeping this. And this is the reason why we have learned something called a big transistor. If you look at the analysis where we have started with, so we have learned two kinds of topology, where one topology says that two transistors are in cascode, one is NMOS, one is PMOS, and one topology where two transistors are available somewhere else, right? They are not shorted. So for such kind of things, it's ID1 minus ID2 are known to us, or they are connected with these equations. Wherever in this case, both the transistors will have same current, which is ID, and that ID is very simple, K times VGS minus VT square, and it can be termed as a big transistor whose W by L will be found out in terms of K, Kn and Kp, and you can have some equation called K equivalent times VGS minus VT. It's the same equation, it has been written. However, these constant terms or this VT equivalent, VGS equivalent is already known to us, right? It's already known to us. It's not a problem. But here VGSN is this one. Here VGSP is this one. Between here to here, between here to here, right? So if that is the case, which we have already found out, through which we can keep such kind of setup where we will make sure that this will give you such kind of control where those floating voltages are not floating, but you are going to add some load afterwards, right? So you can have such kind of things. More complicated things you can implement, not only such kind of things, but I'm expecting to have ID1 minus ID2 divided by V1 minus V2, which is going to give you GM. So for that also, look, this is a transistor which is NMOS and PMOS. This is also a transistor which is NMOS and PMOS. The current which is flowing through this one is getting mirrored over here, right? So if this V1 is increasing and V2 is decreasing, because those are have to be differential signal by nature. So if this is happening, this ID1 might be increasing or decreasing depending on what you are doing, and other side it will be like in a reverse way. So if this is positive current, then it's a minus current, or the total current will be same what we are expecting, and that is getting controlled by a negative feedback loop. One side it's positive, one side is negative, right? So this whole loop is actually the kind of Wilson current mirror, where it's a negative current feedback, and we are taking care of id1 minus id2 divided by v1 minus v2. This is taken care by one important thing, which is negative feedback. And when we are doing implementing this complete transistor is a big transistor. It's a big transistor which is not only q1a or q1b, but let's call this one as q1 and let's call this one as q2, whose this part is here, this part is here, and this is id1 and id2. The whole setup was just to make sure that the current mirrored will give you the current which is required, right? So for this one you can write down id1 minus id2 without having any problem, which is same as what we learned, right? You have to replace the values where equivalent, you have to keep the equivalent values, not, so those equivalent values you need to keep from this one. So you can directly plug the equations from here. So this is also one of the way. Yeah.
Q1 is the Q1A plus Q1B.
No.
Bigger Q.
No.
Then
This question I am asking sometimes to some students, but if two transistors are in parallel, then it's exactly 2W by L. If two transistors are in series or like this, then if this gate source, all situations are same, then W by 2L, right? Your length has increased here, but width is same. But if there is a case where it is like this,
yeah.
can I write down this, that it's W by 2L, or can I write down this as 2W by L? No, right? It has to look at all the conditions in terms of voltages. So if I am doing this, then also I cannot say that it's same, or in this case also I cannot say that, because it's one is NMOS, one is PMOS. Similarly, if I'm connecting two transistors, one is PMOS, one is NMOS, having different voltages, one is positive, one is negative, then I can tell this one that it's a big transistor which may be NMOS or maybe PMOS. Maybe. I'm saying this bigger transistor, I don't know what equation it will be or how it's going to be governed. So, what I'm saying here, if there are two transistors, look at the this sign. Both our sources are sorted together, and such kind of transistor, I am saying that it's equivalent to one big transistor NMOS whose equation is known to me. Any NMOS I know the equation, or for any PMOS I know the equation. For NMOS the equation for ID is nothing but mu and Cox and all these things, but instead of that I am going to write down K equivalent times VGS equivalent minus VT equivalent, because VT will also change. I know this. So if I am making this assumption, then I need to find out what is going to happen or how I am going to make these two circuits equal. For that, I need to find out all these coefficients. For that, I have only one fact which is known to me, that current flowing through both the transistors are same, and the current which is flowing through this transistor is equal to ID is equal to Kn times VGSN minus VTN square. For another transistor which is PMOS, I know that Kp times VSGP plus VTP square. These two equations are already known to me. And I want to map this equation to this one. If I am going to do this, I am going to get K equivalent and VT equivalent both in terms of NMOS and PMOS parameter. So it's not equivalent to two transistors in series or parallel, but you have to find out some different equation because it's NMOS and PMOS, right? I'm keeping apple in the same same place. I'm keeping orange, and then I'm trying to compare, right? It's something like that. So if they're same, then it's okay. You can find out and you can say that it's a big transistor and it's Qn plus, like Qn plus Qp is equal to big transistor Q, but that's not the correct thing. You cannot do this, right? Because they are different by each other in terms of mobility, and that's how the current is changed, current equations. Otherwise, as per this KCL, from the same branch the current has to be same, and that is the equation we have, through which we found out Kn VGSN minus VTN square is equal to Kp VSGP plus VTP square. Both are equal. If you are doing that, then you have to equate all these things and you have to find out, and like, but they are not equal to this equation. These two equations are not exactly equal to this equation. Only the current which is flowing through both the side are equal, right? And by keeping those equations, you can have few parameters which you need to keep it keep it here, where this is exactly similar configuration which we have seen just now. Rest of the things are taking care of. Look, from here to here, it's a current mirror. That's it, nothing else. This is just a current mirror. You can make this mirroring through different business also, like not only Wilson, you can use other things. You can use regulated, you can use triple cascode, whichever thing you want to use, you can use it, right? So this is just how you can make some different combination which is going to give you better output, where K equivalent Q is nothing but 1 by root Kn plus 1 by root Kp. Or maybe I need to look at that because I don't remember. So Kn Kp divided by, so it's Kn Kp divided by root Kn plus root Kp square. So it's coming from here. I'm not going into too much detail of these circuits because it's actually not part of the course. I'm touching it because just for the completion, right? Otherwise, we can drop this also. But those who are designing GMC filter, they have to do this. What I'm doing right now, right? Okay. So bipolar transconductors based on fixed resistors may be made tunable by cascading them with a adjustable gain cells. This is one of the key point which has been kept here. So when it's saying that cascading them with a adjustable gain cell means you are connecting this with a adjustable gain cell, right? So when I'm doing this, I can have such kind of things. Maybe we can talk about this maybe later, right? Maybe tomorrow. Otherwise, it's too much for you, right? Too much analog is not good. But are you following this till now? The main agenda is how to get the linear relation. If you want to have linear, you can use source degeneration through which you can have I by V, I out by V in is nothing but 1 by 2 by GM plus RS, which is source degeneration resistor. But now the problem is how to make that. So if you want to implement this, you can use a normal MOSFET where this may be tunable. You can use this one, NMOS in PMOS parallel. When you are doing this, the whole business is about current. How much current this is going to get. If you want to make the whole thing linear, you have to understand two facts. You may have possibility that there are two transistors which are cascaded, and there are two transistors maybe or may not be connected by some voltages, but their currents are ID1 and ID2 for different values of voltages at gate side. You are going to have, and here it's same in both the side. When you are doing, if it is same, the current is actually because of this entire setup, it's KQ times VGS equivalent minus VT equivalent square. VGS equivalent is already known to us, which is between here and here. K equivalent is already known to us, K and Kp divided by root Kn plus root Kp square. And similarly, VT EQ is VTN minus VTP. That you have to plug and play. This is the thing. So using these like informations, we are designing a bigger system where we want to make the current as constant. For the constant current, you are applying the negative feedback loop, you are applying regulated, all the concepts which you have learned in E512, right? So this is what we learn. Rest of the things maybe we can start tomorrow.